Together, let's take a look at this exact differential equation. We're going to break this down to 3 straightforward steps to make this as painless as possible. Step 1, we want to make sure this equation is exact. So m of xy dx plus n of xy dy is equal to 0 is exact if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. Step 2. So if that's the case, there then exists a function f such that the partial derivative of f with respect to x is equal to m, and the partial derivative of f with respect to y is equal to n. Solve f by integrating m of xy with respect to x by holding y constant. Alternatively, you could find f by integrating n of xy with respect to y by holding x constant, whichever is easier. So we want to find our f, but you're going to get something like f is equal to something plus h of y. So then the issue is finding that h of y, or alternatively finding h of x. So step 3, find h of y by taking partial derivative of f with respect to y, where the partial of f with respect to y is equal to n. And so you will get your h of y, and then you will have, as a result, that f equals something, but that is equal to a constant, a level curve, and that is the solution. So let's work through this. Okay, step 1. Let's just find out if this is exact. So we have this differential equation, and I think a good idea is really just to multiply the entire equation by dx. So we get the quantity x plus y dy, and then if we do some factoring, we get the quantity y plus 3x dx. So that's where the factoring occurred, is equal to 0. So let's take this as n of xy, and this as m of xy. So the partial with respect to x of x plus y is equal to, well, that's just a 1. And the partial with respect to y of y plus 3x is also just a 1. So 1 is equal to 1. We have an exact differential equation. Let's move on to step 2. We'll find f by integrating m of xy with respect to x while holding y constant. And that's just because the partial derivative of f with respect to x happens to equal m. So m is this y plus 3x, So we can say that the partial of f with respect to x is equal to y plus 3x. We'll anti-differentiate. So the right-hand side, we'll get yx plus 3 over 2x squared plus an h of y, and the left-hand side is just an f. Let's move on to step 3 to find that h of y. We'll find h of y by taking the partial derivative of f. So we know f from step 2 is equal to yx plus 3 over 2 x squared plus h of y. So this is because we know that the partial derivative of f with respect to y is equal to Rn. So we'll take the partial of this with respect to y. So yx plus 3 over 2x squared plus h of y is equal to n. So this x plus y is n. So left-hand side, we get an x. It's a partial derivative, so x is treated as a constant. So x plus 0 plus h prime of y is equal to x plus y. The x's drop out. H prime of y is equal to y. Let's solve for y. So we can anti-differentiate h of y dy, antiderivative y dy. So h of y is equal to 1/2 y squared. So now we have our y, or I should say our h of y, if you will. Put this stuff together. So we have f is equal to yx plus 3 over 2x squared plus 1/2 y squared, which happens to equal to c. So this is our solution. It's always going to equal to a constant because we have a level curve as a solution to an exact differential equation. So we broke this down into 3 steps. It's a little bit difficult at first, but if you work through a few problems doing these steps, step 1, step 2, step 3, I think the process will click relatively quick and you'll become a master at this.